Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called top blocks. In this video, we'll learn about Clinojimthompsonite and Chesterite, and then we'll build their crystal structures using top blocks. But to fully appreciate these obscure minerals, we first have to take a quick detour into the history of modular mineralogy.
Clinojimthompsonite was named after Jim Thompson, a geologist with very big ideas on a very small scale. Jim Thompson was one of the first people to realize that many minerals are made of similar building blocks. He showed that the structure of amphiboles can be expressed as a combination of modules extracted from micas and pyroxenes, known as the biopyrable polysomatic series. This concept led to the discovery of the new minerals jimthompsonite and Chesterite in Chester, Vermont, for which Chesterite is named. The most common modular minerals in the Earth's crust are the pyroxenes, amphiboles, and the 2-to-1 phyllosilicates, with the biotite series being a common example. These minerals all look like indistinct black specks in rocks, and the term biopyrable was suggested in 1911 as a non-committal field term. As Jim Thompson proposed in 1970, the relationship between these minerals goes beyond mere appearances. It extends deeper to building blocks at the scale of the unit cell. Here's the crystal structure of talc, which is a 2-to-1 phyllosilicate that has a vacancy or nothing in the interlayer, as noted by a white square. From this structure, we can isolate a formula unit. In this formula unit, there are 3 magnesium sites and 4 silicon sites, which is verified by the formula shown here. Now here's the structure of diopside, which is a pyroxene group mineral. Let's isolate one of these TOT modules and then split it in half to produce a formula unit of diopside. Here, there is 1 calcium site, 1 magnesium site, and 2 silicon sites, which is consistent with the formula of diopside. Now, if we combine a formula unit of talc with 2 formula units of diopside, we get tremolite, an amphibole. This works both in terms of the crystal structure and the chemical formula. In more general terms, the crystal structure of any amphibole can be expressed as a combination of modules taken from 2-to-1 phyllosilicates and pyroxenes. Thompson called this relationship the biopyrable polysomatic series, and he proposed that other combinations were possible, such as 2 2-to-1 phyllosilicate modules combined with 1 pyroxene module.
This prediction led to the discovery of jimthompsonite, Clinojimthompsonite, and Chesterite. Let's explore the crystal structure of Clinojimthompsonite, the monoclinic polytype of jimthompsonite.
Here's the full structure of Clinojimthompsonite, which consists of triple chains of TOT rod modules that are linked by pyrable type linkages. Now we'll take it apart. To learn how to build the component TOT modules of this structure, take a look at the assembly of top blocks video in this series.
To construct the Clinojimthompsonite structure, connect 1 triple chain with TOT module to a second triple chain with TOT module such that the T- of the first module connects to the bottom of the O module. A third triple chain module can then be joined so that the T+ of the first module is joined to the top of the O module. This pattern can then be repeated as necessary to extend the structure. Here, a 4th module is joined to the 2nd and 3rd modules to complete the structure.
Now let's take a look at Chesterite.
Chesterite consists of alternating double and triple chain with TOT modules that are linked by pyrable type linkages. Additionally, after every double chain width and triple chain width pair, the included O modules alternate between using O+ and O-. This pattern results in alternating corrugated layers being visible in the crystal structure.
We will now disassemble it. To learn how to build the component TOT modules of this structure, Take a look at the assembly of top blocks video in this series.
To construct the Chesterite structure, 2 double chain width TOT modules, one O plus and one O minus, and 2 triple chain width TOT modules, one O plus and one O minus, are needed. The T minus of the double chain width TO minus T module is connected to the base of the O minus of the triple chain width TO minus T module. The T plus of the first double chain width module is then connected to the top of the O plus of the triple chain width TO plus T module. The T minus of the final double chain module is then connected to the base of the O plus of the triple chain width TO plus T module. This pattern can then be repeated to extend the structure, and here we'll show 2 iterations of the structure. In summary, the TOT modules are connected widthwise such that the T minus modules join to the bottom of the O modules and vice versa. T plus modules join to the top of the O modules, with the pattern alternating between double chain width and triple chain width modules. And there's also an alternation of the O plus and O minus modules, resulting in this corrugated structure.
Now that we've constructed the crystal structures of Clinojimthompsonite and Chesterite, let's discuss how they correspond to Thompson's predictions. To review, the pyroxenes have single chains and are represented by the module P. When a 2-to-1 phyllosilicate module, represented by M, is added to P, we get MP, which corresponds to the double-chained amphiboles. It then follows that the triple-chained Clinojimthompsonite will have another 2-to-1 phyllosilicate module added to it, thus being MMP. Finally, the structure of Chesterite, which consists of a combination of double and triple chains, corresponds to MP. MMP. In the structure of Clinojimthompsonite, the T sites are occupied by silicon, whereas the M sites within and bordering the O modules are occupied by magnesium and iron. Finally, the spaces between the modules are mostly empty. It's similar for Chesterite, except that Chesterite has 2 different types of sites bordering the O modules, the MD4 and MT5 sites, whereas Clinojimthompsonite only has the M5 site. In this video, we've learned about how modular mineralogical theory led to the discovery of the non-classical biopyrobles, Clinojimthompsonite and Chesterite. We constructed their crystal structures using top blocks and learned about their crystal chemistry.